Thank you for being here. I see there are a couple of new folks, so Don's actually given my talk, so we could turn this into a discussion if you like. But as he said, my task over here is to go into somewhat more detail. And really, what I'm doing here is making an appeal to mathematicians who know more about the particular types of mathematics that we need than I do. So, as Don said, there are 4 of us who've been working on this. So I'm calling this Fusing Agents in Qualia 2, because it is a kind of I'm going more into depth. But the main thing I want to do is to describe some of the mathematics in some slightly more detail, and then request help from people who know how to do it. Let's see, I'm not used to non-Apple computers. There we go. So, because there's some folks who are a little new, and maybe Don also went over his stuff very rapidly, I thought I would review some of what he said, and you'll see many similar slides. So, I'll try to be quick about this, though. And so, we're defining a conscious agent as something that has experiences of the world, and then has a way of acting on the world. Mathematically, this is described as a 7-tuple, where these spaces, the red objects are spaces, they're all measurable spaces, and the mappings between them are Markovian kernels. Okay, so in principle, we can do probability, which is a sort of basic requirement in order to do science. Okay, so the P is a Markovian kernel that takes world states and gives you experiential states, or qualia, if you like. D is a decision kernel, and this is possibly the place where free will comes in. I should have mentioned that word. And that's where the conscious agent makes decisions about what to do about it, or how to respond to its experience. G is a space of propensities for action, and A is a kernel that does the action on the world. Okay, so I already said that. N is an integer that just counts the number of decisions that have been made since the start of the process.
Do you want to just ask a quick break? Is a Markovian kernel the same as a Markovian transition matrix?
Yes, same thing, sorry. Yeah. Physicists would prefer to use the word transition matrix. Or so there are various ways to combine agents in a pedestrian manner, where you're simply putting them together. I mean, it's pedestrian, but it could be very useful. And as Don pointed out, all these ways of networking agents together could be thought of as one big agent. So it's a monist theory. You can have lots of other ways of thinking about agents, agent networks, and so on. But the basic thesis of conscious agent theory, am I going too fast? The basic thesis of conscious agent theory is that the world is made up of, is a network of conscious agents. So it's not conscious agents all the way down, it's just conscious agents interacting with conscious agents. Consciousness interacting with consciousness. Okay. J.D. Salinger had a short story about this. Please remind me to tell you afterwards, because there's not much time. But it's a wonderful, well, okay, I mentioned it. So there's this genius boy who's being transported on a ship back in the day from America to England to study, because he's one of these wunderkinds who at the age of 7 has become like a spiritual master or something like that. And somebody asked him, how did you, what happened? How did you discover that you suddenly had this way of seeing reality? And he said, well, one day I was giving milk to my little brother in a high chair, and I was handing him the milk, and I was pouring it into his mouth. And you excuse the expression I'm going to use just now, but it's Salinger's. He said, and then suddenly I realized that God was pouring God into God. So in a sense, that's a similar kind of point of view, but from a more traditional aspect. Okay, so what we're interested in is actually a more dynamic form of combination, which is combination by asymptotic dynamics of networks of conscious agents. So you look at the long-term behavior of the Markov process that describes the dynamics of the network. And as Don pointed out, this is just one of his slides, which I'm repeating again, is that when you look at the asymptotics, that leads you to understanding decorated permutations, which leads you to understanding, in particular, the Birkhoff polynomial, which is what Birkhoff polytope, which is what physicists use to describe the way in which the Grassmanians give rise to the amplitude hedron, okay, or hedron, or however you pronounce it. And that, of course, gives rise to the known physical world, according to physics. Okay, so very quickly, the dynamics we're interested in is a very simple part of the whole network dynamics. What we're interested in is what does a particular conscious agent experience, what are the dynamics it experiences in its own X. So this particular kernel goes from X to X. B goes from X to G, A goes from G to W, P goes from W to X, so it goes all the way around to X. And so it's on the interface of a particular conscious agent, there will be a dynamics. And we're looking at just that dynamics. So it's sort of like when you're looking at a computer screen, you see the dynamics of things going on in the screen. Of course, you're interacting with it and so on, and then things are happening on the screen. Within the context of conscious realism, which is that everything is conscious networks, the description of physics is what's happening on the interface. And so this particular kernel hopefully will connect with physics. I'm making very broad and provocative statements, maybe we can argue about them later. So this kernel Q is just a kernel from X to X. It's the state space is X itself. And so for example, if the state space is of two things, like red and green, for example, in this case, the kernel will be a Markovian kernel, which means its rows sum to 1. And there's an interpretation of what these numbers mean, that the probabilities of having seen red is to see green is X, and probability of having seen green to see red is Y. Okay, and Don talked fairly extensively about these things in the case of two, state space of size 2. In that case, the parameter space is just product of syntheses, one synthesis. It's a very simple object, it's a unit square. And we've seen how this object functions in the last talk. And one of my tasks over here is to show you how immediately complicated things get. They really develop. Okay, so the Markov polytope that was introduced in the last lecture is a description of all Markov kernels, okay, using X and Y as the parameter space. So we can put it we can picture it in a two-dimensional way. And the main things about this are that the Markov chains that have a particular Markov kernel or transition kernel tend to go along these flows, okay? And if you start anywhere on this boundary, that boundary, or inside, you will flow towards the purple line, which we call the fusion simplex. The Birkhoff polytope itself, this guy, the not operator, it just flips itself. So this guy is a periodic Markov chain, which doesn't go anywhere. But as soon as you get inside, it starts to move there. Similarly, for the identity, nothing happens at the identity, but as soon as you get inside, you get a flow towards this particular point, which is the point which is a stationary kernel. Its powers are equal to itself. Nothing changes. And you can easily see that that means that its rows are the same, 1 half, 1 half, 1 half, 1 half. Okay. The other ones over here on this line are the other different possibilities for the two rows being equal. Okay. And on these boundaries, you see a flow from here towards this vertex. On this boundary, you see a flow from here to this vertex. And the rest of them, you see a flow towards the fusion simplex.
Maybe a quick question. What could you maybe elaborate on what it is that is flowing here?
Okay, excellent question. Sorry about that. I'm kind of bouncing off of the previous talk, but not everything was clear, was remembered from there, right? So what's happening over here is that you're looking at the Markov chain as it develops. Okay, and at the nth stage, the matrix that tells you what the probability, how the probability at the first stage becomes the probabilities at the nth stage is q to the n.
And
So if you look at the sequence q to the n, q to the 1, q to the 2, q squared, q cubed, and so forth, that sequence is flowing.
And is it the state of the agent that we are talking about here, or what? What is the state space of this?
Yeah, it's the probability on the state space of the agent.
Okay, yeah.
Okay. So when we talk about fusion, well, I'll bring that up in a moment. So yeah, it's what is happening to the probability on the state space. If you start off with a probability of say mu, then mu times q to the n is a probability at the nth stage. That's basic fact about Markov chains. So thanks for asking that question. And please do ask for clarification, because the whole idea here is to make things a little clearer, perhaps. Okay, so that's the same picture. I think I'll just skip it. There's a Grassmanian 1-2 is going on over here, but I would mention that. When these flows go towards the fusion simplex, this is where they end up. They end up, for some alpha between 0 and 1, they end up with this particular matrix. Okay.
Sure, maybe.
Yeah.
And so does this mean then that an agent always ends up in some kind of qualia state? Can that be interpreted like this or not?
Yeah. Yeah, it can, definitely. For this particular type of agent.
Okay, yeah.
So, and the qualia state that the agent will end up on is actually, this is that cross-diagonal line. If the original agent saw red and green, the original agents that combined saw red and green, the new agent could see any combination of those two, depending on where it ends up, based on where it started. Okay? So, based on what its Markovian kernel is.
So the qualia of one agent are then also dependent on the qualia of other agents?
Yes, Q includes all the interactions everywhere. It's just we're now forgetting about them in detail, and we're essentially including them all. I don't want to say integrating, but that's essentially what's happening. Yeah. So W, that W, this mysterious thing on top of the triangle, that's all the other agents. Okay. And so there's an interaction, there's an action on the world. Somewhere in the world there's an action on the agent. Okay. And we make a decision, you do an action somewhere maybe else on the world, but somewhere else in the world there's an and all we see of this is what we see on our interface. And so Q describes the dynamics on our interface. From a God's-eye point of view, or, well, same thing, from a scientist's eye point of view, there's this thing is a product of three kernels, but from my point of view, there's just a Markov process going on.
If we compare that to like normal life, I would say that my qualia don't depend on your qualia too much, right? Or
sometimes they do. Right now, they're very highly dependent. I mean, in communication.
But for example, if I now close my eyes,
yeah.
that wouldn't change anything to your qualia, right?
Yeah, sure. There could be non-dependencies as well as dependencies. Absolutely. And yeah, we have to include that possibility. Don talked a little bit about portals of consciousness, and sometimes some things have there's more of a portal, like if I see your facial expression, that's more of a portal. I have some friends who are autistic. When I see their facial expression, it's a little bit less of a portal. They look like they're angry, but they're actually smiling. That kind of thing.
Meta note, so we need to be really on time because we need to switch rooms. So
Good.
you're chairing this.
I'm chairing, yeah.
Oh, so you don't mind. Okay, so I'm going to just zoom through this. John mentioned what happens when you use 3 agents, and so what about when you use n agents? So now I'm just going to talk a little bit about the general case. In the general case, you have an n by n matrix whose rows sum to 1, that's a stochastic matrix. And the set of all these constitutes the Markov polytope, and as Don mentioned, we don't really, mathematicians haven't studied it in much detail. They've studied the Birkhoff polytope, which I'm going to define in a moment. Okay, so I'll skip some of the details here, they're not necessary. It's very important to find out what this polytope is, and is it even a polytope, which means that it's got vertices and flat edges and flat faces and so on, the 2 faces, 3 faces, 4 faces, all up to whatever the n is. And there's a description of, what time do I have to finish?
You still have 10 minutes including questions.
Okay, so there's a way of identifying edges and faces, and there's also a way of identifying adjacencies, which allows you to find the actual edges. Okay, so this is some of this is basic stuff. Everybody knows that in the field of geometry. So the Birkhoff polytope in particular, that was the diagonal line in the M2 case. Okay, that particular polytope consists of the doubly stochastic matrices, and those correspond to ordinary permutations. Okay, it turns out that that's fairly important to physicists because they use it to connect with the amplitude-hedron. Okay, but the Birkhoff polytope is just a one-dimensional segment inside the full Markovian dynamics of just the qualia of one agent. Okay, so this is a much, much richer structure. And if all you get from this today, which, given the time that maybe all you get is that the structure is much richer, then that's great. So the stationary manifold can be defined in a very simple way. It's a set of matrices which are stationary, but that was the off-diagonal line that we were talking about before. And we've already talked about stationary distributions for these. There's some theorems about these which I'm sure have been proven many times before, but I came up with them. We can discuss them later. The fusion polytope. Now, in n dimensions, as against 2 dimensions, something different happens. You end up with not just one fusion polytope, but you end up with n minus 1 of them. Okay, and the flow can sometimes go to the main fusion polytope, which in M3 is just a simplex, a 2 simplex, a triangle. But it can also go to the other fusion polytope, and so I wanted to show you what those other polytopes are also like. The periodicity of certain Markov transition matrices, it also gets much richer, not much richer, but there are many more periodic points. So now we have period 2, period 3 points, and a number of period 2 points, which I will show you on a picture. So the periodic manifold includes the vertex set of the Birkhoff manifold, which defines the Birkhoff manifold, so it's of some importance to the physics, in other words. We've already seen the picture of the Markov dynamics, I'm just repeating it over here. The point up here, the periodic point, is one of the edges of the vertices of the Birkhoff manifold, and the other, that's a period 1 point, the identity, and between them is the convex hull is the Birkhoff manifold. So, what's M3 doing? You saw M2, and here's M3. It's already much richer because they now, instead of 4 vertices, you now have 27 vertices. Excuse me. I just want to show you a little bit about the flows of these Markov processes inside this complicated structure. That's a 2-dimensional version of a 6-dimensional thing. Okay, so this is a listing of all the possible 3x3 Markov kernels. Okay, and what you have at the bottom is the identity kernel, and what we've done over here is, don't worry about the numbers. That's Mathematica, that's Wolfram's idea of what these numbering should be. Okay, but next to this, is the nearest objects to these. These are all, the blue ones are all adjacent to the identity, and then the green ones are further away, and then the red ones are even further away. And these two extreme ones are called are also called derangements. They are permutations. They're in the Birkhoff polytope because we call them sum to one as well as the rows. But they're the level 3 derangements, which means no state goes to itself, it goes to something else. Everybody gets changed. Okay? Yeah. 5 minutes, thanks. So we have two derangements, and then we have which are period 3, and then we have a bunch of period 2 guys. And so I want to talk about that. I'm just showing you some of the structure here. This is a picture of the flow that Don came up with before, and he gave a justification in terms of the two Playvig graph, or what do they call them? Physicists call them, I'm missing it right now, but mathematicians call them Playvig graphs because they're planar and bicolored. Okay, but there's this flow here, and that great triple inside is a simplex, which is the fusion, the basic fusion simplex. Okay, but there's another one. So there's the partial fusion simplex. I've taken the same diagram of all the possible 27 points, and I've put them in a different manner. What's happening over here is that these are the derangements. The identity is sitting somewhere down here. This is the fusion complex. This is the one where all these, where most of the flow goes to. In fact, the entire Birkhoff polytope goes to this fusion complex. But there's another fusion complex. This is the second order fusion complex. And what's happening over here is that these points are sort of bouncing into it and back. So there's period 2 points aside from the period 3 points and the period 1 point. Okay, and this is just a few of them. There are many other points, but the majority of, I mean, all of the internal points in the M3 in the M3 polytope, all of them go to either the fusion complex or to the partial fusion complex. The entire Birkhoff polynomial goes to 1 point in the fusion, in the F2 fusion complex. Okay, so there's some interesting thing going on here. There are different levels of fusion going on, and I think I have to. Here's another way to draw the same picture, which is actually probably should have just shown you this one. The nearest neighbors of these guys, of these derangements, do two different things. They go to two different fusion complexes. Okay, so I'm going straight to.
We have still 2 minutes. Maybe we also want to have some time for questions.
Yeah.
So
So there are lots of conjectures over here. And one of my main appeals over here is if anyone is a mathematician and knows a mathematician who knows more about these things, we would love to find out. Don mentioned that we nailed the decorated permutations in the last 2 weeks. That's not quite true. We nailed it last night. I'll just put the last slide in. What is the structure of higher level MNs? And we want to describe the cell complex structure in terms of decorated permutations. We want to connect it with the Grassmanians. And so really what I'm doing is I'm calling all information geometers, algebraic geometers, and actually anybody. And with a nod to Johannes, with apologies to Johannes, we need you.
Oh, yeah.
Okay. Help. All right, so that's it.